All right, so we'll start with defining standard Young tableau. So a standard Young tableau is a filling of a Young diagram. I think of a Young diagram as kind of a kind of janky upside down staircase. So like our stairs can have like different sizes, but we're just an upside down staircase if we're not familiar with what that means. So we have a standard Young tableau if we're filling with positive integers. Each entry from 1 to n appears exactly one time, and our entries are strictly increasing across rows and down columns. So we have 3 examples here of standard Young tableau. These are going to be kind of one of our 2 main combinatorial objects in this first half of the talk. All right, so we're going to want to look at promotion on standard Young tableau. So this is going to be an action that's going to take a standard Young tableau of some shape and return a standard Young tableau of the same shape. So if we start with the standard Young tableau T of shape lambda with k boxes, here is how we perform promotion. So it's a few steps here. The first thing we're going to do is find where the 1 is. It'll always be in the upper left-hand corner, and we're going to replace the 1 with a dot, as you see here. So that's step 1. And then this dot is going to travel southeast across our tableau, following the following rules. So it's going to look directly to its right and directly below it. And it's going to want to swap with certain entries if it sees those entries in those 2 adjacent boxes. So first, it's going to want to swap with a 2 if it sees a 2 there. After that swap, it's going to want to swap with 3s and then swap with 4s, etc., until we've swapped with everything in the tableau. So we'll go through an example of that. For those of you who are familiar with promotion, this is a little bit of a clunky way to define it, but it's the way that's going to generalize for the second half of the talk. All right, so our dot was looking to its right and directly below. It was first looking for 2s. It found 1, 2. And so the entries in those 2 boxes will swap. So the dot box will become a 2, and that 2 box will become a dot. And then we do the same procedure. Clear. So again, we're looking below and to our right. We're looking for 3s next. We don't see any 3s. So we look for 4s. We don't see any 4s. We're looking for 5s. We see this 1, 5 here. So our entries in those 2 boxes will swap. Then we pick up where we left off. We're looking for 6s. We don't see any. We're looking for 7s. We see this 1, 7 here. So those entries will swap. We're looking for 8s. We don't see any. We're looking for 9s. We see that 9 in the lower right. So those 2 entries will swap. And now our dot doesn't see anything in the tableau. So we're done with the Judith-Takem part of our promotion algorithm. The next thing we're going to do is we're going to put, so k was the largest entry in our original tableau. We're going to replace our dot with a k plus 1. So the next biggest number that doesn't appear yet in our tableau. So we're going to replace it with 10. And then since we wanted to end with a standard Young tableau, we need to have the numbers from 1 to 9. So we'll just subtract 1 from each entry that appears. And that's the promotion procedure. So again, we started with a standard Young tableau of some shape, and we ended with a standard Young tableau of the same shape. One natural question to ask about promotion is, what are the orbit sizes of the standard Young tableau under this promotion action? So let's say that P of T is the result of performing promotion on standard Young tableau T. One thing that's very well known is that if we have a rectangular standard Young tableau, so just like we saw in the last example, and that tableau has n boxes, then if I do promotion n times, I'm going to get my original tableau back. It certainly will happen that it could be the divisor of n will also give you that standard Young tableau back, but we're guaranteed if I have n boxes in a rectangle, then n times promotion will get me back to where I started. Okay, so our second combinatorial objects are called webs. So we can just look at this picture to start. We'll define them, but mostly I just want you to think of these pictures here.
Becky?
Yes.
Sorry, I have a question. I'm just confused about one thing.
Yep.
So you're saying, what are the orbit sizes under promotion? P of t is a result of promotion, blah, blah, blah. It says for rectangular T with n boxes, Pn of T equals T. Now in each step, you're replacing the large, you've got a tableau and the largest entry is K. And then when you apply promotion, the largest entry is K plus 1.
So remember the very last step of promotion, we subtracted 1 from each entry.
Oh, yeah,
so
the very last step, sorry.
Yep.
Right, okay, right, okay, got it.
Yep, does that answer the question?
So you yeah, it does. So you literally mean equal there.
Yep.
Okay, got it.
All right, so these are webs. More precisely, I guess, this is the definition of Greg Kuperberg. We're talking about irreducible webs. So these are planar graphs, so none of our edges are crossing. We're embedded in a disk. The disk itself isn't counting as part of our graph. It's just a convenience, I guess. So the edges along the disk, we don't really think of as edges in the graph. We're not allowing multiple edges. And we're satisfying the following conditions. So we have a fixed bipartite coloring. We can see that each edge here has 1 black vertex and 1 white vertex. We see that all of the boundary vertices have degree 1. Again, we're not counting the disk as part of the graph, so we don't count that as part of the degree. We see all of the internal vertices have degree 3. And the thing we need to be an irreducible web is that our internal faces all have at least 6 sides. In other words, what that means, since we have a bipartite coloring, is that we have no, this is not allowed. We have no internal squares in our graph. So we can have big faces inside, but just squares are not allowed. If there are squares, we can just reduce it down, so it wouldn't be irreducible. All right, so these are what webs are. So just a little bit about why we care about webs. To each web, we can associate something called a web invariant, a polynomial. So let me show you the 2 simplest examples of web invariants for the 2 simplest examples of webs. So I could have a web that's just this one edge with the 2 vertices here. To make an invariant, I need to have cyclically labeled boundary vertices. So let's call this vertex 1 and call this vertex 2. For each of our boundary vertices, we're going to get either a 3-component vector or a 3-component covector. So we'll say the filled in vertices get a vector. So this filled in vertex is going to get the vector x11, x21, x31. And this unfilled vertex is going to get a covector y11, y21, oops, not 1, sorry, that's our second vertex. So we should have 1, 2, 2, 2, and 3, 2. Okay, and then what we're going to do to get our invariant is we're going to sum over all proper colorings of our edges with colors 1, 2, and 3. So in this example, there's 1 edge, so we're going to have 3 proper colorings, right? We can either have this 1 edge have color 1, that's going to give us 1 term our invariant, or we could have color 2, color 3. Once we have the edge colors, the way we get the terms in our invariant is we look around each boundary vertex and we see what color that adjacent edge is. So this edge here has color 1, so that means we're going to take the first component of the vector. So we'll get an x11. And similarly, our second boundary vertex, the edge adjacent to it also has color 1, so we're going to take the first component. And we'll do that for each coloring. So if I colored that middle edge with a 2 instead of a 1, then I would end up taking the second term in each of my vectors. So I'd get an x21, y22, And if I colored that middle edge 3, I'd end up taking the third term. So I'd get x3, 1, y3, 2, which we can notice is just the product of the vector and the covector. So unless I wrote that backwards, I'm not gonna check. But it's the product of the two vectors in one way or the other. Don't make me think about that in front of people. Okay, so that's one simple example. Let's do one, like kind of the next simplest example, which might be slightly more illuminating. Jake, do you have a question?
Yes, just how did you choose the number of colors?
So there's always going to be 3 colors.
Oh, okay.
Yeah,
Got it.
good question.
Thanks.
Yeah, so let's do one more quick example. The next simplest web is called a tripod, and it's just going to be 3 boundary vertices and 1 interior vertex. We need our cyclic labeling of our boundary vertices. Again, we'll have, oops. There's like a slight delay when I write on my screen, and it's messing me up a little bit. So we'll have a vertex at each, or a vector at each of our vertices. And again, we're going to sum over proper edge colorings. With the colors 1, 2, and 3. And like Jake said, we always have 3 colors. So now we have at least something more interesting because we have an interior vertex. So proper coloring actually means something. So let's say we color this edge 1, color this edge 2, color this edge 3. So just like before, I'm going to look at my boundary vertices, look at the edge adjacent to it that has color 1. So I'll take the first component from that vector. My second boundary vertex, the edge adjacent to it has color 2. My third boundary vertex, the edge adjacent to it has color 3. So I end up with this, 2, 2. I end up with this monomial here. And then what I need to do is look around each internal vertex. So we didn't have this step last time. And look at the permutation that I get from those colors. Here I have the identity permutation. I take the sign of that permutation. So that has a positive sign. So I'm getting assigned some of these terms. Let's just quick do one more term here and then we'll see. Let's say we had 1, 3, 2 instead. So I'm taking the first term here, the third term here, and the second term here. And now if I look around that interior vertex, I have the permutation 1, 3, 2, which has negative sign. So we're seeing a little bit more interesting things happen. It's been a long time since I learned this, so I don't know if this is something that people can see without me pointing this out or not, but what we're getting here is the determinant of the matrix if we put all those vectors together. So this is just the determinant of this x11, x12, x13, x31, x32, x33, just the determinant of that matrix there. So this other simple web is giving us just that determinant. All right, so this is what web invariants are. They're called invariants, so they're probably invariant under something. They're invariant under an SL3 action. So the way that action works is I'm just going to take any element in SL3, and then I can multiply my matrix of variables on the left if it's the x variables, on the right if it's the y variables, by that element of SL3, and that's not going to change the web invariant. So we saw, for example, that the determinant is a web invariant. If I multiply by the determinant by something in SL3, of course, that's not going to change the determinant of that. So it's invariant under this action. And more than that, it's actually the webs are going to give us a basis for the ring of invariance. So Greg Cooperberg says, let V be a three-dimensional complex vector space. Then the web invariance I get by fixing a boundary pattern with A white and B black vertices actually form a basis for this ring of invariance. So let me just do a very quick example here. So let's say I want to think about, let's say I want to have two covectors and two vectors, and I want to look at that ring of SL3 invariance. Well, all I need to do is think about all the webs that have two black and two white boundary vertices in some fixed pattern. So I can pick that pattern. Let's just pick like black, white, and I just need to write down all the webs on that fixed boundary pattern. So in this case, that's pretty simple. I think we just have these two webs. And so the claim then is that these two web invariants form a basis for that ring. And I can pick a different boundary pattern and I get a different basis if I pick black, white, etc. All right, so the last brief look into motivating webs. So Sergei Fomin and Pasha Pilyovsky also constructed a cluster algebra structure on the ring of invariance that works well with the web basis in most cases. So anyone who's interested in cluster algebras, there's a connection there too. We won't talk about that anymore here. All right, so finally, let's connect our two combinatorial objects. There's a bijection between webs with n cyclically labeled all black boundary vertices. So we're always going to have these cyclically labeled boundary vertices. In our bijection, we're going to have all of the vertices around the boundary are black. And we're going to biject those with 3-row rectangular standard Young tableau with n boxes. So the number of boxes is the number of boundary vertices. So let me show you how that works. I think it's pretty slick. So let's start with a web that's just big enough to be interesting. Let's take this one here. We need our cyclic labeling. Let me do the same one as in my notes. 1, 2, 3, 4, 5, 6. So this has 6 boundary vertices. So it's going to be in bijection with a 3-row rectangle with 6 boxes. So that's going to be a 3x2 standard Young tableau. And the way we're gonna get our tableau is we're gonna again make a proper edge coloring. Our colors are now 1, 0, and -1. They should have been 1, 2, and 3, but they're 1, 0, and -1. And we're going to try and satisfy the preference of the boundary vertices. So it turns out that a boundary vertex would really like its edge to have color 1, if that's possible. That's its first preference. If it can't have color 1, because that would make the coloring not proper, then it will take 0. Otherwise, it's satisfied with -1 if that's all that's available. So we'll start with our first vertex here. We can give that edge a 1 because there's no restriction so far. So next we're going to look at our second boundary vertex and look at the edge adjacent there. That edge would really like to be labeled 1, but it can't be because we need a proper coloring. So the best we can do is 0. And of course, that's going to force this yellow edge to have color -1 so that we have a proper coloring. And then we're going to continue in that fashion. So the edge adjacent to 3 would really like to have color 1. It looks like that's okay. So let's allow it to have color 1. And now we force this black edge to have color 0 because it's attached to both a -1 and a 1. And that's forcing the edge adjacent to 4 to have color -1. We're also forcing, I don't know if blue is the right choice here, but this middle edge here to have color 1 because that most internal vertex already has a -1 and a 0. So this edge adjacent to 5 wants to have color 1, but it can't. The best we can do is color 0. And that forces the edge adjacent to 6 to have color -1. And now all I have to do is read those boundary edges, and that tells me what row everything goes in. So if I see a 1, that entry goes in the top row. If I see a 0, it goes in the middle row. If I see a -1, it goes in the bottom row. So my boundary vertex 1, its edge has a 1. My boundary vertex 2, its edge has a 0. My boundary vertex 3 has a 1. Boundary vertex 4 has a -1. 5 has a 0. And 6 has a -1. So now I have my standard Young tableau associated with this web. This isn't the original bijection. So the original bijection is by Kovanov and Cooperberg, and they do it using kind of a min-cut algorithm. But this is just a different way to do that.
Becky, a quick question.
Yes.
So I'm not sure if this could happen. So if you look at the field vertex 3, and locally speaking, it can be colored by color 1. However, is it possible that if you look at the whole graph, then this color 1 would like make the proper coloring impossible?
Yeah, so we need to start with vertex 1, and then every time we color something, we need to be sure that we've colored everything that's forced by that. Yeah, so we can't do it locally. We really have to do it globally.
I see. Thank you.
Becky, I also have a question.
Mm-hmm.
So sort of backing up, the two questions I have is, where does the vertex coloring come in these webs? I haven't really seen so far where that's important. Is that just part of the definition, or?
The vertex, you mean the bipartite coloring?
Yeah.
So each of our boundary vertices is representing a vector or a covector. So I think if we think back to like what the webs actually mean in terms of, I don't know if representation theory is the right word, but it matters there.
Okay, matters. Okay, so it's not obvious why it matters.
Yeah, kind of combinatorially, it doesn't matter that much, except that it has a bipartite coloring. But I think if we think about what's going on in the background, then it's meaningful.
So if it has a bipartite coloring, so it's a bipartite graph, and
Don't you have X's for one of the colors and Y's for the other color?
Yeah, so it'll change our web invariance. Yeah. Yeah.
okay.
Yeah, so
Okay, so it's important for that. Okay, so secondly, is it obvious also why we can, when you say proper three edge coloring, you mean no vertex shares two colors on its edges, right? No vertex has two edges with the same color.
Mm-hmm.
Is it obvious that every such web has 3 coloring? Like, so all the vertices are all the interior vertices are degree 3, right?
Mm-hmm.
So I was just wondering, is that obvious that everything has a 3 coloring?
I've never thought about that before. I guess to me, I just took it as fact since that's the definition of the web invariant, but I haven't thought about why that would be true at all. I'm not a graph theory person at all, so.
Okay.
Yeah, interesting question. Yeah, I have never thought about that. All right, so that's our bijection in one direction. I think I'll skip the bijection in the other direction, but it's equally as simple thanks to Juliana Tomatsko. Okay, so now let's connect everything with promotion. So if I start with a web with our cyclically labeled boundary vertices and all black boundary vertices, so those are the webs that are in bijection with the tableau, then the standard Young tableau associated with rotating that web is the standard Young tableau I get by promoting the original. I'll just show you the picture. I should have put this up originally. So I'm starting with some web D, and on the left here, what I'm doing is I'm rotating one, I always say the word click. I don't know. I don't think anyone else does this, but one click counterclockwise. So my red box here is indicating my vertex. That's vertex 1. So what used to be my vertex 2 is now my vertex 1. I'm just like going one click counterclockwise. Horizontally, I just have the tableau I get via the bijection that we just talked about. And what we can see then, well, maybe we can't see it visually, but mathematically what we can see then is that on the right-hand side here, what we're doing is this tableau promotion procedure. So if I rotate the web, that's the same thing as promoting the tableau. So that's pretty handy. This isn't really the motivation for this fact, but we can use this fact then to recover the idea that we're promoting n times a rectangle will give us the rectangle back. Why? Well, our rectangular T is going to correspond to some web that has n boundary vertices. And if I rotate that web n times, I've just rotated it 360 degrees. So of course it corresponds to the same tableau that we started with. So again, I don't think this is the motivation necessarily for the connection, but it's a nice corollary that we can reprove that fact. Definitely not the way it was proven originally. So this is also true in the original theorem, again, we had all black boundary vertices. There is an analog of this for all webs. So we could have black and white boundary vertices. This was first proven by Heather Russell, and then I proved it later in a different way. So she made a bijection between these webs and semi-standard tableau, and then I bijected them with something else. And in both cases, promotion corresponded to rotation. So we do have this result in general for all webs.
Can I ask about this? Because you actually just reminded me, I wanted to ask this earlier when you said the bijection with all the black vertices. I was going to ask for mixed ones, what sort of stuff do they correspond to? So what was your bijection to, if it's possible to state?
Yeah, it is. So if you recall in the bijection that we talked about, we made our proper coloring trying to take into account the preferences, and then a vertex with a 1 edge was in the top row, with the 0 edge was in the middle row, and with a -1 edge was in the bottom row. So if I'm talking about webs with mixed boundary, let's just pretend that this is a portion of such a web.
Is it going to be dominoes or something?
No, well, so what I did is, it's kind of the same idea, except basically I said that white edges corresponded to like going backwards a box or like removing a box. So I would see a 1, if this were my minimal coloring, my preferential coloring, I would see a 1 in the first row of my tableau. And here I see a 2 in the third row, but it's a white 2, so it's going to be like a negative box down there. And then I see a 3 in the third row, so I'm looking at some kind of tableau that looks like that.
Cool.
Yeah, and then Heather just has the semi-standard tableau, so maybe the more natural object. Okay, so we're moving on to part 2 of the talk. So what we want to do is generalize this to increasing tableau. So what I do largely is K-theory combinatorics. So I want to take all this classical combinatoric stuff. If you're familiar, it like corresponds to cohomology of the Grassmannian, and I want to generalize it so that it corresponds to K-theory of the Grassmannian. This is just like most of what I've done mathematically. So that's what we're going to do here. So it turns out the combinatorial object that we want, instead of standard Young tableau, are increasing tableau. So again, we're filling a Young diagram with positive integers. Our rows and columns are strictly increasing, but we're losing that condition that we need each number to appear exactly once. So we're seeing repeats of numbers. we'd still kind of want that standard condition, but there's not really a like convention, like there's not a way to say that in that increasing tableau are these. We want ones that are gapless, so we want that standard condition. Like if a K is there, we want everything between 1 and K to be there. So we don't want any gaps in the entries. So for example, this rightmost one is not gapless because I see a 3, but I don't see a 2. I see a 6, but I don't see a 5. We don't want to consider these because they're not interesting. We can just like reduce to the gapless case. So we'll just consider those increasing gapless tableau. Okay, very quickly, this is kind of what I said, but why would we care about increasing tableau? So they're a K-theoretic analog of semi-standard Young tableau or standard Young tableau. So we can use them to compute the structure constants in the K-theory ring of the Grassmannian. If that's not interesting to you, but you're someone who likes plane partitions, then there's a nice bijection between increasing tableau and plane partition. So all we have to do is on each anti-diagonal, on the first one, I'm going to subtract 1 from all the entries. On the second one, I'm going to subtract 2 from all the entries. On the third one, I'm going to subtract 3 from all the entries, etc. I can get a plane partition that way. And this has been useful at least one time, I guess. I have this project with Oliver Pachenik and Zach Hamaker and Nathan Williams, where we solve a conjecture about plane partitions by translating them into increasing tableau and then using all this combinatorial machinery that we have from that world there. So it is an interesting connection, and that bijection can be fruitful between the two. So that's our brief view into why we might care about increasing tableau. So let's go back. We're just going to kind of repeat the first half of the talk with our new setting. So we have a promotion, a K-theoretic promotion. The way I defined it before, it's exactly the same, which is why I defined it in that kind of funny way for those of you who are familiar. So the first thing we're going to do is replace the 1 with a dot. Our dot is going to look below and to the right. And the first thing that dot is not a good choice. The first thing that it's going to want to do is swap with the 2s. So it sees 2 2s, right? It sees a 2 to its right and below. And so any box that it sees with a 2 is going to become a dot, and any dot is going to become a 2. So they're just swapping the entries there. So we started with 1 dot and now we have 2 dots. So things are a little bit different than originally. So we have that swap there. Now I'm looking, both dots at the same time are going to look to their right and below. They're looking for 3s. So I'll have these boxes will swap and these boxes will swap. Now we're looking for 4s. We don't see any 4s. We're looking for 5s. This upper dot here sees a couple 5s. So the entries in that little triad will swap with each other. Clear. Now we're all looking for 6s. So we see some, so the entries in these 2 boxes will swap, and the entries in this triplet here will all swap. And we'll continue in that way. So we're looking for 7s, we'll get the swap. And they're both looking for 8, so the 8s and the dots will swap there. Next, we replace the dot with 1 bigger than the biggest entry. So we'll put a 9 in that box instead. And then we want to end with a gapless increasing tableau. So we'll subtract 1 from each entry as our final step. So we have this promotion procedure on our tableau. There is kind of a weird case that's going to be an outlier to everything else. So we have this minimal tableau. So each entry here is the smallest that it could possibly be. And this tableau just turns out to be a little funny. If I call this tableau T, then it's actually equal to its own promotion, which is easy to see because this is the only tableau of this shape with entries 1 through 5. So it couldn't possibly promote to anything else. And this is just going to be like an outlier in everything, but it's super predictable. So we're okay with it not following the rules that everything else follows. So we might ask about the order of K promotion on rectangular increasing tableau. So until recently, the state of the art was this conjecture of Cameron and van der Vlos. It said if we start with the gapless rectangular increasing tableau with largest entry Q, then they conjecture if Q is prime, then the length of the K promotion is a multiple of Q, except when that orbit has size 1, which again, that's okay. You know exactly when that happens. So kind of in an ideal world, what you would want is the same result. Oops, not T. We would want the same result as before. So ideally, it would be really great if it were true that if I promoted Q times, Q is the biggest entry, that I would get T back. Here they're saying, well, if Q is prime, we think at least doing it some multiple of Q times, we'll get that tableau back. So Oliver and I were able to prove this slightly more generally. So I'll just very quickly take you through that. So it relied on this intermediate result. So this was a result of Oliver Pachenik from 2017, where he says that that ideal thing that we would really like to be true isn't quite true, but it's like a little bit true. So again, this is what we'd like to be true. Q is the largest entry of our tableau. We'd like to do promotion Q times and get the tableau back. It's not true for the whole tableau, but it is true for the frame. So the frame is just going to be all these outer boxes of our tableau T. So Oliver showed that the frame of our tableau is the same as the frame of the tableau I get by promoting Q times. So that inside might change, but that outside does what we want it to do. And this is basically all that we need to prove this generalization of their conjecture. So let T be a rectangular increasing tableau with largest entry Q and K orbit of size K. So our Q no longer has to be prime. That's the way in which it's a generalization. Then we showed that K and Q share a prime divisor. So if Q is prime, then K is a multiple of Q. More generally, if Q is not prime, they're just not relatively prime to each other. So using that frame result, there's not actually much to do here. What we're going to do is look at the promotion orbit. Let's suppose that the orbit size in Q, the largest entry, are relatively prime. Let's look at our promotion orbit and let's just kind of draw it around a circle. So I'm going to have T, P of T, P squared of T. Eventually I'll have PQ of T. And we'll kind of just do the orbit around in a circle like that. And what we're going to do is start at T, and we're just going to bounce around the circle doing Q times promotion around the circle. So I'm going to do promotion Q times. That's going to get me to PQ of T. I'll do promotion Q times. That's going to get me to P2Q of T. And since Q and K are relatively prime, if I'm bouncing around by gaps of Q each time, eventually I'm going to land here at P of T. So the promotion of T is actually some multiple of PQ of T. Okay. So what that means then, using Oliver's result, is that the frame of T, each time we do promotion Q times, the frame stays the same. So everything we've bounced to around this circle has the same frame. So we've shown that the frame of T is the same thing as the frame of P of T, because we eventually landed here in P of T. It just turns out that this is a really rigid condition, and it's not too hard to see that if you promote your tableau and have the same frame, that actually implies that those two tableaux are equal. And the only time that T is equal to its promotion means that T is that weird case that we don't really want to think about. So the only time when our result isn't true is that weird case, and that's okay, because then it's true every other time. So that was pretty cool. We have that result, and at this point, I guess this is the state of the art of what is the orbit size here. Computationally, the orbit sizes are kind of crazy, and we don't know what's going on at all. Like any pattern you might hope to find, we haven't found. All right, so just to end, we talked about in the first half of the talk, well, if I have this promotion, maybe I can like make up some webs, and then rotating the webs will correspond to promotion, and then I'll know something about the order of the promotion because I know something about rotating the webs. So basically, that is what we would like. So we conjecture that the K promotion orbit of T has cardinality dividing Q. So basically, like I said, wouldn't it be nice if we could make some webs that correspond to the increasing tableau so that rotating the web corresponded to promotion, and then we would know something about the order of the promotion. So this is kind of our current work here. What we're working on here. So with Oliver Pachenik and Jessica Stryker and Juliana Tomatsko, we're trying to define the proper K analog of webs for an increasing tableau. So we end up with pictures like this. We have some kind of multi-edge situation going on here. So we've been thinking about this for a while. I think we decided that this project was a little too ambitious for where we were at after months of kind of going around in circles. So currently we actually just reduced it down to the 2-row case, which I haven't really discussed here, but in the standard setting, a 2-row tableau is corresponding to a non-crossing matching, where promotion of the 2-row tableau corresponds to rotation. If I replace a standard tableau with an increasing tableau, I'm getting a non-crossing set partition, where it's also known that the promotion corresponds to the rotation, but there's just a lot of other details in this setting that are unknown. So we're trying to fill in all of those so that we can use that information to help us build the 3-row case. So that's the current state of what's going on with this. Yeah, so that's
yeah. Thank you so much, Becky. It's really very engaging and fascinating talk. So if you can, please unmute and clap for Becky. And I think there might be some question in the chat. And also, if you have questions, please ask. So I have one question. So is it possible to sort of modify the structure of the web, like allow the internal vertices has degree 4, 5, 6, and so on? In that case, could you like do like 4 coloring or 5 coloring, something like that?
So what I know about that is, so what we're talking about are called SL3 webs, because we got those SL3 web invariants.
Mm-hmm.
There are people who study SL4 webs and SLN webs.
Okay.
So like an SL4 web would have internal vertices having degree 4,
I see.
etc.
Okay.
Yeah, so that is something that people study, but it's not, it gets way harder. Like they don't have a basis basically. So they know what the webs look like, but they don't have nice web bases in those cases.
Yeah, I see. Gotcha.
I have a question. For the slide where you said that like everything goes wrong with the orbit lengths, and I guess, so other than the fact that the orbit lengths are multiples of Q or share a factor with Q, can you say like what, like, so when you say everything goes wrong, what do you mean? Like there's no upper bound, you know, they're like, I don't, et cetera.
Yeah, so no upper bound. Like I gave a version of this talk yesterday and Maria Gillespie asked like, well, you know, they're not relatively prime. Like, do you know what prime factors they have? Like, no, we just don't know anything. And mostly Oliver's been doing the computations, but like nothing seemed like we haven't made sense of any of the computer data that we
What
have.
about like existence then? Like, does your data suggest that like there exist certain, counterexamples to like, can you definitively rule out any of these statements, or is it just like even too messy to speculate on that?
As far as I know, we can't rule anything out, but again, Oliver's the one who's really been looking at it, so I can't say for sure.
Okay, so if no more question, let's thank Becky again. And I believe Becky has something to show with her experience at University of St. Thomas.
Yeah, well, so I'm happy to talk about this. I don't know
let
if
me
people.
stop recording.
Oh.